Hey man, did I put like ideal inverters on the output so that it was nice logic signals or? So here's what we should do. Let's come back over here real quick. And then maybe, I don't know. Copy. Okay. All right. Has anybody had any classes canceled this last week? No? You have? Classes canceled? All right. Oh yeah. Problem fixed. All right. Um, no finals, right? Wait, what is this one you're talking about? Um, you did something wrong. I don't know. Let me see here. I don't know. Don't know. Yeah. Well, I mean, it's the finicky thing of LT Spice. So, which actually it's nice that you have LT Spice because you can work at home, right? Well, and also, yeah, you had to be here the last 3, 4 days. What's that? Yeah. Well, no, if you try to run it, it's not that you can run it from home. It's just not practical because of the if you run Cadence because of the internet connection and the speed. So, all right. Okay, so one of the things I'm going to do right now is make sure that I'm going to ask you questions and I want you to think about the answers because I want you to do well and I'll get hundreds on the projects, all right? I'm not going to try to trick you, but I want you to follow what's happening. Okay, so, oops. And if I ask you simple questions, especially when I've asked them today and you can't answer, that's a problem. All right. Okay. This is chapter 9, mixed signal. I don't know what the date was. No, the lecture number, sorry. All right, so in this thing, there's a couple of things that we need to notice. One, as you know, we care basically about the edges, but since the topology in chapter 9 is a switch capacitor topology, we have to ensure that the clocks that we use are non-overlapping. So what we see here is we see a pulse width, which is, I don't know if it's, well, it's not here, it's not shown as 50%, but What we care about is for this timing is the difference between the edges. And so as you know, if you have a frequency of 100 megahertz and you have k paths and k is 8, then this ends up giving us a, whoops, I need to multiply this. This ends up giving us a new frequency of f sub s nu. So one of the questions I'll ask you when I'm going through your projects with you is, on your project, how does this pulse width or duty cycle influence the performance of your topology? And if your answer is it doesn't, then I'm going to ask, okay, why? And then you're going to need to coherently explain to me why the duty cycle doesn't influence the performance of your topology. Now, if you understand what's going on, that's not a challenging question. If you don't, we'll find out. Okay. Another question I'll ask is, I went through and I did the clock generator design, and I don't, unless you did something special, I think the one I came up with, the duty cycle wasn't 50%, if I remember, was it? No. So, okay, so then I ask, all right, so if I go in and I look at the delay stage and I say, okay, here's your inverters, here's your NAND gate, what happens to the duty cycle if I change the connection of the NAND gate, or where this is going from, say here to here, and you go, oh, it'll change the duty cycle. Then I'm going to ask why. Okay, so I'm not going to ask you hard questions, but you can't just go, oh, it's clocking, and not understand you need an odd number of inversions or trivial questions like that, all right? I'll also ask you, okay, did you try to run your clock generator slower? Okay, if it runs slower, what is your concern and what are your thoughts? What are you worried about? And then you might, well, you tell me, what would be some of your concerns? If you run your modulator slower, what would be a concern? No, not the sample rate. What? No, I mean just that it works. I mean, obviously the bandwidth is going to shrink if you clock it slower, but what's the big circuit problem that you have to worry about? Well, can I run, let's say I have the topology running at effectively a gigahertz. Can I drive it down to run at a megahertz? No, why? I can in the switch capacitor, but I can't. What? Well, I mean, but what's the issue? What's the problem? Give me a qualitative, this is what I'm talking about. What's the problem if I run real slow for a continuous time modulator? No, close. The integrator is going to saturate, right? The integrator is going to overflow. If you let the signals go a long time without changing them, the integrator is going to charge up. So you have to change your integration capacitance or your resistances to larger values so your output of your integrator doesn't saturate. That's the level of question I'm going to ask. I'm not going to ask you, like, okay, if I put the pole here and I move it by 0.01%, I'm going to ask you questions that say, okay, well, what happens if I run this slow? What happens to the integrator? What happens to the the overall feedback signal, those kind of things. Is anybody unclear about integrator saturation? Another one I might ask you is, okay, well, why is the comparator offset not such a big deal, but the integrator, the op-amp's offset is a big deal? Yeah, exactly. Yeah. Yeah, so the comparator's offset's referred back through the integrator's gain. The integrator's directly added to the input signal. Okay, again, not trying to trick you. Okay. Any questions on this? Okay, so one of the things that we have to worry about is the settling time of the op amp and the feedback signal. And what I'd like you to understand or be able to kind of qualitatively describe is you have this RC time here that's not ideal. It's not putting a chunk of pulse that goes like this. Why or why isn't that an issue? Okay, and give me a qualitative explanation. So first off, everybody understands, well, let me ask a simpler question. What is slew rate? What is the, if your op amp's showing slewing, what's the problem? Yeah, so if I have an op amp and I've got my output here and I'm seeing slewing, show me what you're going to see over here. Yeah, it's going to be like a straight line where it can't keep up. It's slewing. All right, it's not going to be a charging and discharging like I see there. So if it slews, that's a big problem because you're not linearly adding or removing charge. You're adding charge depending on an amplitude and how fast this slews. Okay, so we want to say slewing doesn't happen in our op amp topology. Okay, so if I look at the output of your integrator and I'm saying slewing like this because you got a current source that you put in here or something like that, that's a problem. Okay, question? Nope. Okay, so slewing is bad. Now, when I have finite bandwidth, what does that manifest itself into in a simple example? It means here I'm not able to empty my cup before the next pulse comes in or before I start removing it away. But if it's consistent and I always empty 2/3 of the cup, I always have this much charging, then it's okay. So now let me explain the difference between this and slewing. If I have an RC circuit, right, and I put a pulse in here and the pulse goes from 0 to 1, and I ask you, how long does it take the output to go to 1/2 volt? What's the answer? So the output does this. Yeah, it's 0.7 RC. It's basic RC. It's 0.7 RC. Okay? If I change this to 10 volts and I ask you how long does it take to get to 5 volts, or again half the waveform or half the cup, 0.7 RC. So effectively, when you have these finite bandwidth problems, they're going to limit how fast or how much of the water you can dump out, but they're going to be consistent from time to time. Okay, as long as your cup size is staying consistent, even though you don't dump it all out, you're still going to have an okay operating modulator. You'll just get a gain error. Now, what does a gain error mean? A gain error means that instead of getting out something like this, you get out something like this, but it's still linear. And if it's linear, that's okay. It's not going to introduce distortion. What's the problem is if it becomes nonlinear, then it affects your signal-to-noise ratio drastically. Does that make sense? Wenlan? No? Here, another example. If I have a gain error, I get out a sine wave that looks like this. If I have another gain error, I get out the same sine wave but with a different amplitude. Okay? If I look at the spectrum of the sine waves, one has an amplitude of this and one has an amplitude of this, but I have no other noise or distortion in the spectrum. I'm just changing the magnitude of my signal. Remember, the criteria for distortionless transmission is constant amplitude. You have your system here. You have an input x of t, and your output is y of t, which is equal to k, some constant amplitude, times x of t minus t0, where it's just phase shifted. And that's the definition of distortionless transmission. Constant amplitude could be not 1, but it still doesn't introduce distortion, and a phase delay of t0. Does everybody follow this? Okay, so doing this isn't a problem. It's when I start to slew or other things change. Okay, any questions? So before I move on, so if we have f sub s is our sampling frequency and we have k paths, that's equal to fs new. Does everybody agree with that? So in the MATLAB scripts, you had a couple of things. You had k, or k path. Then you had another thing. Yeah, OSR. Okay? That's the sum of the product of these two is your overall amount of filtering, right? Your over sampling rate. Does everybody follow that? So I'm going to show you that on the next slide. Yeah, k path times k is equal to OSRs. Did I not say that clearly? Is that what you're saying? Yeah. Yep, that's right. Okay, so So I've got f sub s new, which is what? And so here's my filter that I'm plugging in, and this gives me my f sub s, my desired spectrum. The bottom line is that I'm going out to f sub s, and then repeating rather than, I'm sorry, f sub s new rather than f sub s. Okay, so if I were to ask you, give me an example of a filter that implements this transfer function. A counter, a sync filter. Again, not trying to trick you, but I don't want you to pass the class if you can't answer that level of question, okay? Or if you go, I don't know exactly what you mean by that. I have never seen that filter before. All right, so here's the switch capacitor version. Now notice one thing different is that the clock phases are now non-overlapping. Here is a output filter, and if I ask, if so, say what, here's one thing I definitely want you to be able to answer. In the MATLAB script, what's the difference between serial mode and parallel mode? Why do you get higher signal to noise ratio in signal series mode rather than parallel mode? Yeah, you throw in the order, right? And another way of answering it is you're applying a filter to all of that data and decimating, and that decimation is causing noise to alias in your base spectrum. Does everybody follow that? So when, Len, you're going to be able to answer what's the difference between serial mode and parallel mode? And give me a simple example. Here, let me give you an example. 1111000. Okay? 10101010. In parallel mode, I add up the number of ones and divide by the total number. I get 1/2. Parallel mode, I add up the number of ones, divide by the total number, and I get 1/2. These are different signals, right? So they're different signals. If I look at them as they're coming out at a real high speed rate or in serial, then I get a different response between the two. When I add them all together, I'm effectively decimating the output because it's coming out after 8 samples. And so with decimation, I'm going to get a little aliasing, and that's going to increase the noise. Yay? All right. You're going to be able to answer that? Okay, we'll see. Because it'll last a lot longer if I start asking you these level questions and you can't answer them, all right? Any questions on this topology here? All right, and just to show you the response, there's the 5. And if I were to ask you, well, isn't this a multi-bit modulator? Because if I look in chapter 7 at the output of the multi-bit modulator, it looks exactly the same here. What's the difference? What's that? No, this is the output of the adder. So you could say, yeah, you're decimating. But what's the difference? I'm so glad you asked. Isn't the KD1S94 simply a multi-bit modulator, section 7.3.4? First, the ideal, okay, make sure you know this, all right? Because when you look at, this is something someone could ask you. When you look at the multi-bit modulator, you're using, 7 comparators, and in 8-path you're using 8 comparators. Well, aren't they exactly the same? When I look at the outputs, they look the same to me. Okay, so go through and make sure you understand the difference in those topologies, all right? Any questions? Because when you add them together, the output of the multi-bit is, here, let's look at a multi-bit to answer that question. what is the multi-bit output? It is 7.45. Okay, so what I'm going to look at here, notice this output can only have discrete amplitudes, right? 0, since it's 16 levels, it would be 0, 62 millivolts, 128, etc. If I go back, this has discrete amplitudes, just like that, but my output's only going to change in those discrete steps. So when I look at the output, and it would be better if I put a 3-bit in there instead of 4-bit, so you would have bigger steps. Imagine the steps doubling there in size. You really can't tell the difference because both are outputting the average, right? And so they look basically the same. Does that make sense, or do you want me to try to? I don't think I have a 3-bit in here, do I? Yeah, that's what I'm thinking. Is just get rid of this dude. All it's going to do is make the amplitude, step amplitude, bigger. So there you have it. Now we're going a little too high for that step, but you can see it's kind of the average, right, as we're moving up and around. And then if you look at the output here, you get similar kind of behavior. And the difference is, in one case, we're taking one word that's clocked at every F sub s, and here we're having the sum of the bits change, which are running average like a thermometer code, so it's not the same. Okay. So I'm not going to really, I'll just touch on this. Does everybody understand that if you can do different things, like you have different registers, like here's the register with clocking everything out to the summing circuit, so you're decimating by K. Here's where you break it out and you sum, and half the cycles you sum, and the other half, so you're decimating by K over 2. And then you could also chunk them out and then read them out serially. Are there any questions? Okay, so here's what's in my mind. They all know this. There's nothing here that I'm boring them. But if I'm wrong, then you need to tell me. Eon, make sense? All right, kind of hiding back there. Okay, so let's look at the output. There's your KD1S modulator. And you got your 8 bits coming out here. You resynchronize, you add. What does this do here? When you resynchronize all the bits at once and add them together? Decimates, yep, and filters it. And then we go over to my little filter here, that's my comb filter. Then I've got another comb filter coming out, which chokes the bandwidth back down. And so this doesn't give you as good a performance as taking the data out serially and using it that way. Okay? And then if you would like, we can look at the simulation results. I'm just going to throw this up briefly. And then let's talk about different filters. Now the problem here, okay, you tell me, what's the issue here with the input signal? The filter that I just showed you, what's the fundamental problem? Yeah, the filters, I mean, we're getting a fast sample rate, we're attenuating it, and it's rolling off our input signal. Everybody follow that? So now what we want to do is investigate other types of filters. And so we'll go through, and I'm going to go through these briefly and just talk about it. Here's one that's decimating with the filter that we talked about in 6.25. So the nice thing here, so again, one of the problems we have is we're decimating and adding all the bits together. We're not getting a serial output. So immediately that handicaps ourselves. And not just as a sanity check, did anybody run MATLAB and get higher signal to noise ratio on E knob with a parallel output when compared to the serial output? Sometimes. Well, I mean, when the stuff you turned in, did anybody get that? No. Right? Yeah, if you run the simulation, so you look at it and you go, oh, okay, here's my simulation, and then you say green, and then noise. So this is out of the band or whatever. What is the proper term? Out of bandwidth. What's that? No, I mean, but what was the label in the plots? Oh, greater than B. So if you do that and you run a short simulation, your signal to noise ratio is going to shoot up artificially high, right? All you're going to see is green and then nothing, and there's no noise in the spectrum where you're calculating SNR. Okay, that's not good. I'm sure nobody did that, right? I got signal to noise ratio, SNR. That's what I got. My design's rocks, man. Okay. You got to have points of noise in here. If you don't have points of noise, you're going to have a real high signal to noise ratio. Well, no, if you go to the longer times, you have to simulate longer. That's the problem. Because if you don't simulate longer, you don't get the points in the lower spectrum. If you don't have the points in the lower spectrum, when it adds up the power in those, there isn't any, and that's the noise. And then you get your signal is this, and then noise is basically 2 points or whatever it is, or none, and so you have super high signal to noise ratio. Okay? All right. And so here's what happens when we redesign the filter without as much attenuation. And gee, it looks better. It's not as attenuated. And then we say, okay, well, what happens if we don't decimate right at the front? And so instead, what we're going to do is we're going to ping pong back and forth. And the whole point of this figure is that when you're doing designs in hardware, it's really easy to do something and not realize your signal, your DSP, you're manipulating or filtering your signal. So here's a simple example where I said, I'm going to take 4 bits out, and then the other cycle I'm going to take 4 bits out, and then I'm going to add them together out here. And when you do that, when you add these 4 bits with these 4 bits, that's a 1 plus z to the minus 1, which has a frequency response that looks like this. It's an averager. And then that gives you, I mean, it's going to be wider bandwidth than what we had before, but it's going to influence your frequency response, and then you use the filter that comes out. The problem here is if you don't design the filter correctly, after this stage, you won't attenuate the noise, and you'll get something that looks like this. And that's not good. Okay. Similarly, any questions there? Similarly, if I take the output and I go, okay, well, what I'm going to do is I'm just going to run it straight through the filter without, just the sync response filter and my adder here without really paying attention to the bandwidth. Am I going to remove the quantization noise? And the answer is no. You still have lots of noise, and that's you see right here in the circuit. So let me go back real quick to figure 910. Where's figure 910? Right here. So then the question might be, okay, well, how can we modify this with out decimation? So in other words, okay, so I just said that. What does that mean? What am I, if I'm not decimating, what am I doing? Well, I'm doing serial mode, but I'm also not clocking or lowering the clock frequency in these stages or the clock's frequency in this stage. And if I do that, of course, all the simulations are available online, I get something that looks like this. Now, what's the input frequency here? Because before I had a larger signal, but my input frequency was only 6 megahertz or so. Now I've increased the frequency to 50 megahertz. I see the attenuation, but it's still much better than what I had with the 6 megahertz. Okay. And so the whole key point is that you got to know when you're messing with the digital bit stream what you're adding and getting the bits out do. And then also you have to know how to design the filter so you can remove the modulation noise. All right. We're going to go real fast through these next several things. So here's a single modulator with a clocked at 100 megahertz, and I'm looking at the output spectrum. So if this was something similar to this was in your report, and I asked you, why is it repeating? Why do I have this shape of this wavy shape here? What's up with that? And you're plotting the noise transfer function. Why isn't, I'm used to it going up and stopping. Why is it continuing out to 800 megahertz like this? Yeah, it's a sampled system. It's a trivial question. It's a sampled system. Any sampled system's frequency response repeats at intervals of f sub s. I hope we went through the unit circle enough times. No, we're rotating around and around and around and around. Everything repeats, right? So that's what we're seeing here. So we're starting out with a single modulator showing the spectrum out to 800 megahertz, but it doesn't actually stop. It keeps going, repeats. Any questions on that? Right? Why? Well, we're just rotating around the unit circle. Okay, so what happens if then I say, well, let's try to improve speed by putting the modulators in parallel. That's where we take Z and replace it with Z to the number of modulators in parallel. Let's say 8 here. Okay, and you ask, well, what happens when you do that? What happens when you do that is that you get a reduction in the amplitude of, because you're increasing your sampling frequency, get a reduction in the peak amplitude of the noise as seen here, but it continues going out. If we just drew the noise transfer function alone, it continues going out forever just like before. In other words, we're not getting true noise shaping. So putting modulators in parallel doesn't give us true noise shaping. Is anybody not clear on that point? When you put this through, what we want is we want to have noise that does this, right? So that when we pass the signal through our filter, we have less noise. And what we have when we do this is we have the comb filter where it repeats, and we still have a significant noise there. In other words, it's just lowering, by putting multiple paths in there, we reduce our quantization noise. We reduce the peak quantization noise by the number of paths in parallel, but we still get the rippling effect. In other words, we don't get true noise shaping, which does this and repeats at f sub s nu. Okay? Does that make sense? Yeah. So the point here is that you can't just take the digital systems and put them in parallel. So, and this whole branch of digital signal processing is called polyphase or multiphase, because poly and multi, polygraph, what's that? Multiple graphs. Polyphase signal processing, we're doing things in parallel. All right. So what is and I know all you native English speakers don't answer this, but what's the colloquial term for a polygraph? What's the common or colloquial name for a polygraph? Here, write it down. I never thought I'd write this in a lecture. What's a polygraph? Do you guys know? Why did I change the record? It's recording.
Why did you change the Greek word?
Oh, what is the Greek word? What? I don't know. It's the term, who wants to tell them? Yeah, it's a lie detector. So when you say that you're, oh, I didn't commit that crime, they put you on a polygraph or a lie detector.
They don't do that. They don't do that anymore. Actually,
I
it's
know.
not admissible as evidence.
Right. Well, I don't think it ever was. What was that?
We know from the TV series they use polygraphs in movies and series
Yeah, yeah, yeah.
and on
I
talk
kind of
shows.
thought you guys would know. What's that?
And on talk shows, that's the best part of the talk shows.
Oh. When you said that, I'm thinking of the Japanese game shows where they. You ever watch those YouTube videos? All right. So anyway, poly, multi-phase, you have your little phases of signals going through. All right. So I want to talk briefly about circuit stuff. Okay, so here's a delay element, and I ask you, okay, how do I know this provides non-overlapping clocks? How do I know phi1 and phi2 are non-overlapping? Okay, or let me ask a simpler question. How do I adjust the period between the clock signals? What's that? Yeah, I put more inverters here and here, right? If I move this out, let's say I did this, what would happen? Yeah, it would be instead of being like this, it would be, you get more delay between the signals. So what does that do if you're trying to get 50% duty cycle? Yeah, it goes the other way. It goes the wrong way because you keep putting more and more delay there, and you'll end up with a situation where you have something like this, right?
But it eliminates clock skew though to stick the feedback all the way at the output. So it's more decisive.
Um,
But you have more delay elements, so the variance is divided by the number of delay elements per clock jitter.
all right. I'm just saying that you should have plenty of decisiveness if you put two regular inverters there. And you guys say that you didn't. Somebody did this. You did, and you like better. Okay. But I mean, if I ask you, okay, so what's the problem with putting that, or what happens to the delay to the 50% duty cycle? You say, oh, it makes a 50% duty cycle poorer. And I go, is that a problem? No, it's not a problem in my design. Why? Because I care about the edges between here and here, and this is what I'm feeding back. All right, but I need to be able to ask you questions on that and know that, oh, I didn't just, unless you've not taken the circuits class, then I have to, be understanding there.
I think if you're gonna try and use transmission gates, you'd want those edges to be really decisive.
Yeah, you want them to be fast, and you want it to turn things on, and you want to feed back a nice square signal, so you want as much drive as you possibly can. And I think that's fine. It's just if, and this application obviously doesn't, if you needed a 50%, you should know it makes it less 50%. It's not a problem, and I did it for this reason. All right. I guess the bottom line is I don't want to get in there and start asking you guys questions. You go, I don't know, I don't know, I don't know, I don't know. I want you to be able to give me some thoughts on things. What's that? Get used to it? Uh, I have high hopes. All right. Let me see. Where I want to go to. Uh, yeah, I don't want to cover these things. This circuit, one of the big things here is uh, you don't have slew rate limitations, and so that's one of the big benefits of using this topology. But what's the big drawback? Yeah, the gain is low, right? It's high speed, doesn't have slew rate, but the gain is not good. And if you, well, the out minus isn't going to swing much at all, right? Yeah. So I got a question. Why not just put two of these in cascade? That's not a question I'd ask you unless you've taken the analog class. Yeah, stability. It's too hard to make it stable. You put the capacitor around the overall topology, the delay through the forward path is too long and it'll make it impossible to stabilize the op amp. Don't believe me? Try it. You don't want. Yeah, what's that? You tried it? It didn't work? Of course it won't. All right. Um, uh, did anybody use this comparator? How'd it work? When, Lan? Used a different one? Okay. Well, we'll see what you did in your project. The what? Jerry? Oh, Jared. Like, who's Jerry? Okay, so you used his comparator, and it was better than this one.
I used that diff amp that I showed you that I found on. Well, there was one that you designed. I think I included that in the schematics, and then there was one that I used that I didn't put into the simulation, but it's in the font. It's in the directory.
Okay.
So,
But I mean, bottom line is the comparators, were they a problem in general?
well,
What's
I never changed it.
that?
The inputs don't switch or really low voltage.
Yeah.
So I had to preamp to let those out.
Okay.
So
All right.
the delay through it was the problem with the computer itself.
Well, yeah, the problem is, like you were mentioning, the squaring up the signals here. This part you would like to get rid of it, but you really need it to get real decisive square signals out, and also so that they don't change.
Yeah. If you're using like a 100 megahertz clock, then you'd have what, like 1.25 nanoseconds worth of path delay, and that I think that one gave you 800, 900 picoseconds of delay or something
Okay.
to stuff lower.
Did anybody try it without these?
No, I could have tried that without it.
All right. All right. Let me see. Anything else here? Okay. So when I go through your projects, if you if you did everything with one sine wave, that would be a problem. You got to put some other signals in there, like different frequencies, a ramp, a DC, something like that. If your only experimental results is here, I put in a sine wave at 3 megahertz and I simulate it for 3 microseconds or something, that's not really characterizing it, all right? So nobody did that though, right? What? You wanted other signals besides that 3 megahertz? That's not right. You should ask for that. Oh, I did put it there. Okay, all right. Yeah. I was waiting for somebody to say, "No, I only use that one sine wave." What? You didn't tell us. Oh God. All right, that's all I have. Does anybody have any comments or questions? All right, so what are we going to do on Wednesday? We shall, let's check. Review for the final. And I hope this one's a fast one because I hope you feel that you've learned something in the class. Although, since you're not getting to do a teaching evaluation, you may hate the class and you'll never know what you'll ever know. But I'll talk to Cameron again and see what happens. So let's call it a night.